In basic electronics, very often you have to deal with a network of resistors, that is, multiple resistors making a circuit with a battery, and in some cases, multiple batteries. And there are basically two approaches to solving these networks. So when I mean solving a network, I mean finding the voltage across and the current through each one of the resistors in the network. So the first approach, and actually the approach that I generally recommend, is to, of course, draw the circuit and then to figure out the total resistance of the entire network and the current coming from the battery. And then piecemeal, resistor by resistor, figure out if you know the voltage across it or the current through it based on the current information that you know, and going from what you know to what you don't know. Now, if that sounds a little vague, it's because each circuit is going to be different, and it almost becomes like a puzzle. But I feel like when you do it that way, you actually understand the circuit because you've analyzed it piece by piece. The other approach is to use matrix algebra in conjunction with Kirchoff's laws to solve the network in a very methodical way that works with extremely complicated networks, and in some that's actually impossible to do using the puzzle approach, but is a little more rote, a little more mechanical, but also very reliable. So let's go ahead and analyze the circuit using both methods so that you can see them in comparison and make my vague statements here a little more concrete. The circuit we're going to analyze as an example has a 9-volt battery in series with a 1,000 ohm resistor, and this is followed in series by 3 resistors in parallel with each other, 2,000, 5,000, and 10,000 ohms. So let's go ahead and draw it. Now we're going to tackle this the way I like to call the puzzle approach. And the puzzle approach always starts the same way. We're going to figure out the total resistance of the entire circuit as felt by the battery. So in this case, we have R2, R3, and R4 in parallel with each other. We're going to find the resistance of that parallel combination and add it in series with R1. The combined resistance of resistor 2, resistor 3, and resistor 4 is 1.25 kiloohms using the parallel addition rule. And that's in series with R1, so R total of the entire circuit is 2.25 kiloohms. And therefore, the current flowing from the battery is the voltage of the battery divided by the entire resistance of the circuit. 9 volts over 2,250 ohms gives us 4 milliamps. Now we go ahead and we look at our circuit and we say, what can we know? We know that that current, 4 milliamps, flowing through the battery also must be the current flowing through resistor 1. So we can immediately say that I1 is equal to 4 milliamps. From that, we can apply Ohm's law to resistor 1. V1 is equal to I1 R1, and figure out the voltage drop of resistor 1. So we have 1,000 ohms times 4 milliamps gives us 4 volts. So we have a voltage drop of 4 volts across resistor 1. We had 9 volts from the battery, so at this point, the voltage of the circuit at that point relative to ground, the negative end of the battery, is 5 volts. And because resistors 2, 3, and 4 are in parallel with each other, they're connected to this 5 volts and to ground. So V2 is equal to V3 is equal to V4, which is equal to 5 volts. Now that we know the voltage across each one of those resistors, we can say that I2 is equal to V2 over R2, Ohm's law. So we have 5 volts over 2,000 ohms, gives us 0.0025 amps, or 2.5 milliamps. I3 V3 over R3 is 5 volts again, divided by 5,000 ohms, which gives us 1 milliamp, and I4 is V4 over R4, which is 5 volts over 10,000 ohms, which gives us 0.0005 amps, or half of a milliamp. So you can see that that was fairly quick for a simple circuit. Now, for a very complicated circuit, this can be very time consuming and it's easy to make a mistake. But it's a good approach for simple circuits, and 95% of resistor networks are going to be fairly simple, because our goal, normally we're not making complicated resistor networks. We're putting other things in there, capacitors, diodes, and whatnot, and we don't have pure resistor networks all that often. So, but let's go ahead and look at this circuit using the matrix algebra approach. I'm going to erase everything, and we're going to pretend that we don't know any of this. The basic idea behind the matrix approach is that we have a system of equations, and we have 8 unknowns, in that the currents and the voltages across each resistor are unknown. But we're going to treat it as a system of 4 equations. We're going to try to write everything in terms of the currents only, I1, 2, 3, and 4. And when we do that, we will end up with this equation, where the little tildes underneath mean matrices. So, well, let's just dive in and we'll see how it looks. First off, here we have a junction, and so we can immediately say at that junction, at the Kirchoff's junction rule, the currents flowing in is equal to the currents flowing out. I1 is equal to I2 plus I3 plus I4. So that's coming from our junction rule. Next, we're going to apply Kirchoff's voltage rule, or the loop rule, and we have 3 loops here. We have loop A, we have loop B, loop C. So for loop A, we can say that 9 volts of the battery minus the voltage drop of resistor 1, so 1,000 ohms, I'm not going to write the units, I1, minus 2,000 times I2 is equal to 0. For loop B, 5,000 times I3, voltage drop across resistor 3, minus 2,000 times I2 is equal to 0. The negative sign there is because my red arrow indicating the direction I'm going in my loop. So going from here around, I'm going against the arrow. So it's actually a voltage rise here. And loop C, we have 10,000 times I4 minus 5,000 times I3 is equal to 0. So let's go ahead and write these 4 equations in a format where each one, just to be absolutely clear, has I1, 2, 3, and 4 in it, with and on the left-hand side, with constants on the right-hand side. So there's our junction rule equation, written with all the i's on the left. Let's go ahead and do the same for loop A. And loop B. And loop C. Finished our setup, we can go ahead and write the matrix form. So again, our matrix equation, A times I is equal to B. B is a constant. And so what we have here are going to be, our top row is going to be 1, minus 1, minus 1, minus 1. Second row, 1,000, 2,000, 0, 0. Third row, 0, negative 2,000, 5,000, 0. And the last row, 0, 0, negative 5,000, 10,000. And our matrix I is a column matrix, column vector, I1, I2, I3, I4. The matrix multiplication gives us the matrix on the right-hand side, 0, 9, 0, 0, 0, 9, 0, 0. Now that we've set up the matrix equation, all we have to do is that I, the solution that we're looking for, the currents through all 4 resistors, is equal to the inverse matrix of A times B. So what we're going to do is we're going to pull over a calculator and input the matrices so that we can let the calculator do the matrix inverse. Okay, we have the matrices entered, and so now all we need to do is tell it that we are going to take the inverse of matrix A, and we're going to multiply it by matrix B. And so our 4 currents, I1, 2, 3, and 4, are 4 milliamps, 0.0025, amps, 2.5 milliamps, 0.001, 1 milliamp, and 0.0005, half of a milliamp. These are all in amps. So at this point, we can simply multiply each one by its resistance to get the voltage across. And I'm not going to bother including that here in the video, but the voltage across the first is going to be 4 volts, 1,000 ohms times 4 milliamps. And 2,000 times this will give us 5 volts. 5,000 times that gives us 5 volts. And 10,000 times that gives us 5 volts. So we can see immediately that the voltage across resistors 2, 3, and 4 by the matrix algebra turn out to be the same voltage. So here are the 2 methods. You see the puzzle approach and the matrix algebra approach. Again, for a simple circuit like this, I would recommend using the puzzle approach, but for very large networks or ones in which there may be some connections that are bizarre, the matrix approach and using Kirchoff's laws that way may be the better way to go.